Good morning, my dear students. From today onwards, for a few days, we are going to learn something about what's called genetics. What is genetics? Genetics deals with the inheritance and variation. It deals with the inheritance and variation. Okay. Now, the word genetics was not derived from the word genes. Most of you think it in that way, but the word genetics was derived from the word genesis. Genesis means development. You would have heard about these two terminologies as spermatogenesis, oogenesis, etc. So, genesis means a development, not the subject which is dealing with the development of character, development of the morphological organs, anatomical organs, physiological organs, etc. Everything. It is called as genetics. So, genetics is the study of the inheritance and variation. So, inheritance is the process by which characters are passed on from parents to progeny. It's a basis of heredity. Variation is the degree by which progeny differ from their parents. So, we inherit certain characters from our parents, but at the same time, it doesn't mean that we should lifelong possess that character. It undergoes certain variations due to the environmental changes or environmental problems. Any character is subjected for variation. So, the inheritance and variation put together, that only develops a particular character. So, a character is developed both by the genes as well as by the environment. So, genes, when it is developing, it is called inheritance, and when there is a change, it is called as a variation. Now you are able to see the beautiful photography of one of the greatest scientists who has ever lived in this world. His name is Johann Gregor Mendel. He is considered to be the father of genetics, or you can call him even the father of classical genetics. The biography of Mendel is very interesting. Even though Mendel is being studied only in botany and zoology a lot, he is not at all a biologist. He was a mathematician. He had his BSc degree in mathematics. He was working as a mathematics teacher in a school, opening school, and then he thought that he should change his or switch over his job profession. So he wanted to specialize on theology. What is called theology? Theology is the study of the religion. So not like now present days. In those days, if you want to study theology and if you want to have a priesthood, you have to undergo a rigorous training for more than 10 years. But he did that. So he studied theology, philosophy, and then finally he became a father or a priest in a church. At the same time, he didn't leave his teaching profession also. He wanted to equip himself with other subjects, namely physics, chemistry, mathematics, and also a little bit of biology. So all the informations that he gained throughout his lifetime from physics, chemistry and mathematics, this helped him a lot in becoming a very great scientist of that time. Okay. So in the course of lecture you will see that or you will understand that if Mendel was not a mathematician, he would not have arrived at the conclusions that he arrived. It is only his mathematics knowledge which helped him to get these conclusions. So his mathematics knowledge helped him a lot in understanding certain biological principles. In fact, the mathematics applied to biological science became a separate subject after some time, and that is what is called as a biometry. Biology plus statistics is called as a biometry or biostatistics. It goes by different names. Okay? Now we will learn a little bit about the biography of Mendel. It's very interesting. Gregor Johann Mendel was an Austrian monk. Austria is a place in near Czechoslovakia. It is one of the European countries. He was the first one to explain the mechanism of a transmission of characters from the parents to the offsprings. He maintained that there were particles called factors which carried the traits to the subsequent generation. Now, before the period of Mendel also, people were thinking, they were constantly contemplating over the fact, what is responsible for the transmission of the character? Which is doing this wonderful job of transmitting a character from one generation to another generation? How a cat is able to give rise to a kitten and a dog to a puppy and not the reverse form? When a woman gives birth, she doesn't give birth to a monkey, but she is giving birth only to a baby. How all these things is taking place in nature? It is because of the genes, it is because of the heredity. And this heredity or these genes he called as factors. But you know, before the period of Mendel, people had wrong ideas about the transmission of the characters. And if you just read some of the textbooks, you will be able to understand how many theories were there. There were what is known as pangenesis theory, and then particulate theory, vaporization theory, like that. Many theories were there explaining about the transmission of the character. But none of the theory has got scientific validity. And they were not able to prove that a particular theory is right. But it is only the experiments conducted by Gregor Johann Mendel which gave you a concrete and clear proof to show that the characters are transmitted from one generation to another generation through what are called as factors, which we now call as alleles, and which in turn is called as genes in fact. Even though he was able to prove in black and white, he was able to publish it in the form of the papers, everything was scientifically done, but still people were not able to understand and appreciate the great work of Mendel. That you will see during the period of Mendel, his work attracted only very less attention. Nobody was ready to accept his work. Only after the period of Mendel, what we call as a post-Mendelian work, people like Schermak, Correns, and all these people, they unearthed the work of Gregor Mendel, and then they found out that there is a substance in that. And what Mendel told is absolutely, totally correct. And then they repeated some of the experiments done by Mendel, and they found that absolutely they were all fitting in a correct fashion. So at the time of Mendel was not at all recognized. After the period of Mendel, he was fully recognized, and we give him today the credit of what is called as the father of genetics. This holds good even today, and since that is what this holds good means, the transmission of the character from one generation to another generation is taking place by the factors. This is what he told. Okay? Now that holds good even today, and since he is a pioneer of modern genetics, he is called a father of genetics. Gregor Johann Mendel was born in 1822. Please note down. To a family of poor farmers in Silesian, a village in Heinzendorf, which is now a part of Czechoslovakia. After finishing his high school at the age of 18, he entered the Austrian monastery and at Bren as a priest. From there, he went to the University of Vienna he went to the University of Vienna for training in physics, mathematics, and natural science. Here he was influenced by two scientists, Franz Unger, a plant biophysiologist, and Christian Doppler, the physicist who discovered Doppler effect. And he himself became interested in the hybridization experiments. Now I have to talk a little bit about these hybridization experiments. You will be really amazed to understand that his father was a plant breeder. And it is in the previous slide you have seen that he is born to the poor farmers. So his father himself was a plant breeder, and Mendel learned the technique of a plant breeding from his father. See, hybridization you and I can't do all of a sudden. It needs a lot of what is called as training, and you can only trained people can do it. See, hybridization means you have to see in most of the situations you see the flower as a bisexual flower, okay, and then that bisexual flower will be having the androecium and gynoecium. First you have to decide which one you want to make use as a male flower and which one you want to make as a female flower. See, the flower or the plant which you want to use as a male flower, you have to collect the pollen grains. It's a very tedious job. It is a time bound. It's not a tedious job, it's a time bound activity. Because I have already explained to you that the dehiscence, the anther is called as anthesis. And anthesis duration, it remains for 3 to 4 days only. Once the anther is mature, it will be liberating the pollen grains, and the whole process will remain only for 2 or 3 days. And within that 3 days, you have to collect the pollen grains. Otherwise, it will get mixed in the air, and you will be able to see only empty bags there. Okay. We used to say that the early birds catch the worms. Like that, you have to go early to collect the pollen grains. If you are going late, you will be able to see only the empty bags there. So all these activities were time-bound activities. And then which flower or which plant you want to use as a female, then you have to carry out what is called as an emasculation. Now you have to cut down all the stamens. This is done by several techniques. Sometimes you have to use a small scissors to cut all the stamens. Sometimes if the flowers are very small, minute, as in the case of the inflorescence of a sugarcane, maize and other monocotyledonous plants, each inflorescence will easily contain 10,000 to 20,000 flowers. Then emasculation becomes totally impossible in these cases. Then what do? You follow different techniques. Hot water method, by treating it by chemicals, etc. Whereby you will be killing all the pollen grains. Okay, so the anthers are virtually removed by means of scissors and forceps, or by suitable techniques you make a flower, a female flower, by a technique called emasculation. And then the other flower which you are using as a male, you have to collect the pollen grains, and then you have to dust these pollen grains to the stigmatic surface, and then you have to bag the whole gynoecium, because once you do the hybridization, foreign pollen should not come and sit over the stigmatic surface to contaminate it. Otherwise, the whole experiment goes wrong. Okay. So what you do is then it has to be bagged. After bagging, when the seeds are set, after 3 or 4 days, you can remove the bags. You have to remove it. Otherwise, the development of the seed and the fruit will not be in a normal way if the total span of a fruit development, the seed development is going to be within the bags. So you have to remove the bags after some time. Okay, so this is what is called as a hybridization technique. So first making one flower as a male flower, other as a female flower. The one which is used as a male flower, you have to collect the pollen grains. The one which you are using as a female flower, that you have to do the emasculation. and then you have to bring both the plants together by means of a dusting the pollen grains to the stigmatic surface, then making the plants to set the seeds, bagging, and then finally collecting the seeds and then sowing the seeds to see the result. So these are all the techniques involved in the hybridization. As I was telling you, Mendel got this technique learned from his father because his father himself was a farmer and a very good plant breeder. So he himself became interested in hybridization experiments. The findings of Mendel and his laws were published in the journal Annual Proceedings of the Natural History Society of Brunn. Brunn is the place where he was living. Brunn is the name of the place. So from that place, journal was published, and the name of the journal is Annuals of Proceedings of the Natural History Society. In those days, history, see, the term history is used in a very loose sense. Even biology was once upon a time called as a natural history, and then they changed it as a natural science. Then the name changed as a biological science. Then it became a plant science, animal science. It's all changing of the terminologies. So natural history is nothing but has nothing to do with the real history that you are studying today in your school. Natural history means biology. Okay. So Proceedings of Natural History Society of Brunn in 1865. The paper was entitled Experiments in Plant Hybridization. But his work was not accepted. See, this is what I was mentioning a few minutes back. His work was not accepted or lauded by the scientific world at that time. See, when you live in a particular time, and when you preach something, when you say something, people are not ready to accept. This holds good not only for Mendel. It's a general statement I am telling you. It happens in the case of anybody else. When Christ was there, nobody appreciated him. But after that, we accepted him as a God. When this happens everywhere, this happens in everywhere. When Socrates was there, when great people were there, when they were telling and teaching something, when Mahatma Gandhi was there, he was preaching so many things, but he was not accepted during his period. But later on, after 50 years, after 100 years, we realized that what they told is correct. This holds good in Mendel's case also. When Mendel, with all his effort, with all his hybridization, procedures and techniques, he was able to come out with the 4 laws which I am going to discuss elaborately: law of unit characters, the law of dominance, the law of segregation, and law of independent assortment. He was able to prove that, but still nobody was ready to accept his views. This is what is happening in the case of many scientists. Mendel conducted cross-breeding experiments in the garden pea, that is a Pisum sativum, is a botanical name for the pea plant. It belongs to the family Fabaceae and the main family Leguminosae. Leguminosae is the main family because all the plants coming under that category is producing a fruit called a legume. Okay. And once at a particular stage it was divided into 3 subfamilies. Now each subfamily is elevated to the position of a family. One is called as a Fabaceae. Other one is called as a Sasalpinaceae. And the third one is called as a Mimosaceae. So Fabaceae, Sasalpinaceae and Mimosaceae are the 3 families of the Leguminosae, and the Pisum sativum is coming under the family called Fabaceae. He crossed 2 pea plants with contrasting characters, considering one character at a time. The resulting hybrids were crossed with each other. Okay. The data of many crosses were pooled together and the results were analyzed carefully. A combination of luck, very important, foresightedness, and the aptitude to carry out the experiment, and his interest in mathematics, his knowledge of mathematics. All these four, luck, foresight, aptitude, and his interest for mathematics. I have divided the third point into four. These four things contributed to the success of the mentor. Okay, we will discuss this a little bit more, because why they have given, sir, will luck play a role in science? What is this? You see, luck is something different, and how a luck could play a role in the science? Yes, I tell you, it's yes. Many times, luck is also playing a role. I tell you, if Mendel had not chosen Pisum sativum as his experimental material, he would not have got the particular result. Because, Pisum sativum is containing 7 pairs of chromosomes. So 2 in number is equal to 14. 7 pairs of chromosomes it is containing. And fortunately, Mendel took 7 characters for his analysis. And most of the characters that he took were on different homologs. See? In one homolog, one character was there, and in another homolog, another character was there, and in a third homolog, third character was there. Sometimes 2 characters were present in 2 homologs, but in most of the cases, each character was present in one homolog. Now, had they been present in the same homolog, any 2 characters represented by a particular gene, if they had been in the same homolog, it would have become a case of linkage and not a case of independent assortment. Only when the 2 characters are present in the 2 genes in the 2 homologs, then you get the independent assortment. These 2 go into one pole, these 2 go into one pole, these 2 go into one pole, and these go into one pole. Independent assortment. Whereas here, if both the characters that he chose, if they were present in the same homolog, he would not have got this 9:3:3:1 ratio. He would have never got it. He would have got some ratio in the linkage, which we will be discussing at a later stage, say 47:3:3:47, or some other ratios, but he would not have got this. This ratio you get only in the independent assortment. Independent assortment, it takes place only when the 2 characters are present in the 2 genes located in the 2 different homologs. So this happened in the Pisum sativum. Had he chosen some other material as his experimental material, definitely he would have landed only in utter confusion. Total calamity, total confusion would have been there. Mendel would not have arrived at the conclusion so easily. That's why we say luck. Mendel was really luck in selecting the Pisum sativum. Perhaps that was the plant which was growing at the backyard of the house. So that's what we say. I should say that it was a sheer luck for Mendel for having selected Pisum sativum as his experimental material. Foresightedness, very, very important. See, he selected 2 pair-breeding varieties. A tall variety and a dwarf variety, a round variety, a wrinkled variety, a green variety and a yellow variety. Like that, he selected contrasting characters, and he anticipated, he wanted to know what will happen if these 2 plants differing in one character is crossed. So this anxiety, this anticipation, this foresightedness was there for Mendel. Then and his aptitude, he had a great aptitude for the test. I tell you, he started his breeding experiment somewhere when he was nearly about a 27 or a 30-year-old man. And till his death, he was continuing his experiments on the Pisum sativum plant. Okay, so consistent work. He has worked nearly for about 20 or 25 years. Till his death, he was working on that plant. So, an aptitude for the plant botany, an aptitude for the hybridization, aptitude towards the genetics. This interest was there. And then, above all, his knowledge for mathematics is more important in arriving at the conclusions. So, for example, when he got the result, 3:1 ratio, when you sow nearly 400 seeds, and when you say that the tall and the dwarf plants are produced in the ratio of 3:1, when you conduct an experiment, these seeds or the tall and the dwarf plants will not be in the ratio of 300:100. No, they will not be like that. See, there will be always a deviation from what is called as a rule. This is a rule. When 400 plants are produced in the fifth generation, it is in the 3:1 ratio. That's what Mendel says. And if it is going to be like that, then you can't expect them to be 300 and 400. But somewhere it may be 280 and 120. If we were there in the place of Mendel, we would not have thought that this is nothing but a slight deviation of 3:1. When he sorted out all the ratios, all the characters for the tall and the dwarf, yellow and the green, round and wrinkled, axillary and terminal, inflated ovary and constricted ovary, like that, when he calculated the total number of plants in the F2 generation, when he scanned through the result, it struck his mind that it is a more or less a 3:1 ratio. That is how he came to the conclusion. If Mendel did not have that mathematics knowledge, this would not have reflected as a 3:1 ratio, but it would have looked just like a mere number. Only if you are getting 300 plants and 100 plants, 300 tall and 100 dwarf, it looks like a 3:1 ratio for us. But even this is a 3:1 ratio for a mathematician and for the people like Mendel. So his mathematics knowledge helped him to arrive at the conclusion. So only when he came to the conclusion 9:3:3:1 is coming, he found out that the total of that is 16. And when 16 zygotes are produced, how is it possible? He took the square root. So 4 male gametes and 4 female gametes should be responsible for that. He came to a conclusion. If 4 gametes have to be produced by 2 homologs, then independent assortment must take place. It is to that conclusion he is coming. He is deriving by that logical argument. He is getting the things by a logical argument. And these things are possible. This logical derivation is possible only for a mathematician, pure mathematician. So, as I was telling you, his foreluck, foresightedness, and his aptitude and his mathematics knowledge, all these things helped him to arrive at the correct conclusions. He conducted hybridization experiments in two breeding parents, individuals which produce the same type of offspring for any number of generations when selfed. So here I am using the word selfed, and in many places I have used the word hybridization. So I'll just going to explain certain things about that in the after some time until I go toggle presentation after finishing this slide. Mendel worked with 7 pairs of contrasting characters and considered 1 pair of the contrasting character at a time. That's very, very, very important. Even though he was doing a dihalved cross, he was considering only 1 character. He never confused 1 character with another. It was very clear in his mind that he is looking for only 1 character at a time. Okay, at a time he was working on only 1 character. So even though he took two characters simultaneously, he was looking for it from a different angle. See, roundness is a roundness, and the color is a shape is a shape, and the color is color. See, a color can never be mixed with a shape. This idea he had very clear in his mind. So he never confused, or he never, he never told that the characters will be mixed. Okay, so he mentally worked with the 7 pairs of contrasting characters and considered one pair at a time. That point is very important. Now, I will go to some terminologies. I will try to explain to you now. See. Okay, this is one. Now I have written 4 type of, or 4 process I have written here, and we use different terminologies for this. Yeah, pure breeding tall variety is taken, and then it is a cross with a pure breeding dwarf variety. You need not use the word pure breeding dwarf variety, it's a dwarf variety. Only here you get the hybrid tall variety and a pure breeding tall variety, but still doesn't matter. So you take a tall variety and then cross it with a dwarf variety. Okay, so now this is what is called a monohybrid cross. I am crossing 2 plants differing in one essential character. Okay, so that's what I am doing now. Now, what is this called as? What is this called as? Now, this is called as hybridization. Hybridization. It is called as hybridization. Sometimes you see the terminology, there will be different terminologies for genetics and for agriculture. In agriculture or in genetics we call as hybridization, but in agriculture they are generally using the word of crossing. They are crossing. When you take 2 plants differing in one essential character, and then when you bring the pollen grain of one with the another, or this whatever it is, then it is called as hybridization or crossing. Now, this is what is called as selfing. This is called as selfing. So it is also called as self-pollinating or self-fertilizing. Selfing the plant, or self-fertilizing the plant, or self-pollinating the plant, any terminology you can use. Now, what is selfing a plant? You take one plant and cross it with the same variety. In fact, it is not a crossing. You take the pollen grain from one plant and dust it over the stigmatic surface of the very same plant. Here the plant, I have written twice, but the plant involved is only one. No 2 plants are involved here. That is why it's called selfing. You collect the pollen grain from this plant if it is a male plant, if you are going to use it in that way, and then you dust it over the stigmatic surface of this one. Then that is called as a selfing. Okay, now when this F1 hybrid is crossed to its dominant parent, then what is this called as? This is called as dominant backcross. This is called as a dominant backcross. When a hybrid is backcrossed to its recessive parent, you call it as a recessive backcross. Recessive backcross is also called as test cross. This is another word. That's also called as a test cross. Okay. So these are all the different terminologies that we are using for the different type of plant breeding techniques that we are following. When you make such a cross, it is called as a crossing, and this is called as a selfing. This is called dominant back cross, and this is called as a test cross or a recessive back cross. Why you call this as a recessive back cross or a test cross? I give some explanation. When you take a plant, F1 hybrid plant, when you have got a plant of this nature, okay, and then you want to actually you don't know the genotype of the plant. What you are seeing is only a tall plant. Fine. You are seeing it. You are going to a garden one fine morning. You are going to the garden. You are able to see a tall Pisum plant. Okay. Now you are interested very much in its genotype. You are interested in genetics. So you want to find out the genotype of this plant. So genotype of this plant is of two types. One is called, this could be like this, or it could be like this. This is also a tall plant, this is also a tall plant. This is a homozygous tall, this is a heterozygous tall. Okay. Now, if you want to know whether this tall plant is a homozygous tall or a pair breeding tall or a hybrid tall, what you have to do, see, if you take this plant, and then cross it with this plant. Because you know this plant is a dwarf plant, and you have got a ready stock of the dwarf plant there. But instead of crossing this tall plant with this, if you choose to cross it with another tall plant, now what happens? You don't know the genotype of this tall plant. See, the problem is here, you want to find out the genotype of this tall plant. In an attempt to find out the genotype of this tall plant, if you are going to cross it with this tall plant, the genotype of this tall plant is also not known to you. How can you solve this problem? In mathematics, in a simple language, it is an equation of two unknown. See, you write x plus y is equal to 3. Find out the value of x and y. If somebody is telling that, he should be a fool. See, x and y, you have got two unknown things, and the value is given, one is a 3. So any value could be given to x and y. X could be 2 and y could be 1, x could be 3 and y could be 0, x could be 1.1 and y could be 1.9. It could be anything. It could be anything, I tell you. So, if you have got two unknown, you can't solve the problem. Similarly, you want to find out the genotype of this tall plant. And in an attempt to that, you are crossing it with another tall plant. So, the genotype of this one is also not known to you. So, if you want to test the genotype of a particular phenotype, you have to cross it only to the recessive parent, because you know the genotype of this parent, because the dwarf plant can have only this genotype. It cannot have two genotypes as this plant. So if you want to find out the genotype of a particular phenotype, you have to cross it with a recessive parent and not a dominant parent. So crossing a hybrid to a recessive parent is called as a test cross. Now you understand why a recessive back cross is called as a test cross. It is used to test the genotype of a particular phenotype. It is used to test the genotype of a particular phenotype. That's why it is called as a test cross. Okay. So now in this I am giving you some of the crossing techniques. This I have already explained to you. But anyhow, I will just give you a faster reading. Since garden pea is self-pollinating, great care was taken to see that the parents were emasculated. Removing the male sex organ is called emasculation. Removing the male sex organ is called emasculation. So removing the whole stamen completely, or the anther, or the pollen grains, whatever it is, to prevent the self-pollination. The anthers were collected from the male parent and dusted onto the female parent, and the stigma was bagged. The seeds were collected separately in marked bottles. Reciprocal crosses by interchanging the male and the female parents were conducted to prove that there was no change in the ratio of the offsprings. Sex has no influence on the inheritance. This reciprocal cross, I am going to explain a little bit more to you. What is a reciprocal cross? Now, you see, you take a tall plant and then you cross it with a dwarf plant. This is a tall plant and this is a dwarf plant. This I am using as a male parent, this I am using as a female parent. Tall I am using as a male parent, dwarf I am using as a female parent. Okay, now it's very clear. Now, you know the result, it is giving rise to tall plants. Okay. Now you see what happens when Mendel was explaining about this transmission of the character from one generation to another generation. He is going to explain that factors are responsible for that. Each and every character is controlled by a pair of factors. These factors segregate and then they combine together and then they produce what is called as a tall plant. It is in that way he is going to give the explanation. But there is a danger that people may not accept this view and then they say, no alleles, no allelomorphs, no factors and nothing is there. A male parent will always express himself, because already in the male dominated society before the period of Mendel and the time of Mendel, there was a general opinion that male alone will be able to express the characters and the female cannot express the character. Male alone plays a very vital role in the reproduction and a female, she is only a recipient. Male is always described as a donor. He is donating the characters. Female, she is only the receiving the sperm from the male and she is helping only in the development of the baby in the womb. Okay. But actual contribution of the character is only from the male. That's what people were thinking once upon a time. Now, when people are having that type of attitude, that type of thinking, if Mendel is going to argue that the character is by the factors, then people may not accept. So they will simply say that there is nothing called factors and a male is expressing this character. Now, he want to rule out this. He want to rule out this discussion or this argument or this what is known as argument. So, he did a reciprocal cross for everything. What is a reciprocal cross for this one? You see, this tall plant is taken as a female. This is taken as a female and this is taken as a male. Now, this cross is a reciprocal of this cross. I hope now you understand the thing very clearly. You are using a tall as a male and a dwarf as a female. And then you get all tall in the F1 generation. When you reciprocate it, when you take the tall as a female and the dwarf as a male, even now you are going to get all tall in the F1 generation. Now the people will not argue that male alone will be able to express the character because here the male is a dwarf. Now the argument of Mendel has got what is known as a more strength. So to prove that the sex of the individual or sex is not playing a role in determination or the passing of the characters, from one generation to another generation. He was doing reciprocal cross for all the crosses that he was doing. Any cross that he took, tall versus dwarf, round versus wrinkled, yellow versus green. As I was telling you, any character that he took was doing a cross, and he was doing a reciprocal cross also. And another thing, another beauty about Mendel's experiment is he went up to 7 generations for each and every character. See, he took a tall plant, cross it with a dwarf variety. He got all tall in the F1 generation. Then he inbred this, and then he collected the plants, F2 generation. F2 plants were inbred to get F3, and F3 plants were inbred to get F4. So, how the character is flowing generation after generation after generation, he went up to 7 generations, and then he was trying to locate how the character is flowing. This is what I told him in the very beginning. Aptitude for the experiments, the likings, his constant perseverance, his hard work. This alone resulted in the success of the Mendel, I was telling you. So each and every character he went up to 7 generations, and for each and every character he was doing the reciprocal cross also. So all these things proved beyond any doubt what Mendel suspected to be. He thought that factors are responsible for the transmission of the character, and to prove that he had to do all these things. So this is about the reciprocal cross. Now these are the 7 characters that Mendel chose. See, in the shape of the seed, you got a round and wrinkled, and in the color of the cotyledon, you got the yellow and green. Gray in the seed coat color, you got the gray and white, and in the pod shape, pod means fruit. Pod means not singing. Pod means shape, fruit shape. See, inflated and constricted, and pod color, green versus yellow. Now you have to be very careful in studying this. In pot color, green is dominant and yellow is recessive. And in cotyledon color, yellow is dominant and green is recessive. If a question is asked based on this, 2 plants are crossed, and if an yellow is crossed with a green variety, what you will get in the F1 generation? Don't jump to the conclusion that a F1 generation plant will always be yellow. See whether they are asking the question on the cotyledon color or a pot color. If it is going to be on a pot color, if a green is crossed with a yellow variety, you will get green only in the F1 generation. If the character dealt is a pot color. Okay. So you have to be very careful in this. Similarly, position of the flower is axillary and terminal, and then the height of the plant, it is tall and the dwarf. Now, one thing you should notice here is all the characters that he chose was very clear. No, what is called as ambiguity. No, what is see, even a layman can tell which is a tall plant and which is a dwarf plant, because a tall plant grows for about nearly 5.5 feet height. And a dwarf plant grows up for about only 1 foot, or even less than that, 1 feet. These are 5 feet. So, when a plant is this much height and this height, a dwarf plant, nobody can have a confusion. Similarly, one seed is yellow in color and another seed is green in color. So, yellow and green, nobody is going to confuse. Similarly, one seed is perfectly round in shape, and the other one is wrinkled in shape. So there is no confusion. Absolutely there is no confusion in the characters that he chose. It is one of the very, very important advantage for Mendel. Because if the characters were confusing, then you would not have arrived at the correct conclusion. Okay. So the 7 contrasting characters he took. That's what we mean by the term contrasting. So this picture shows you about the monohybrid cross. So a tall plant is crossed with the the parents. A small mistake has come. Sorry, not a dwarf plant. This is self-fertilization. This is F2 generation. This is F1 plant. Perhaps this tall is this, and this dwarf is this is a little bit missing here. So the tall plant is a cross with the dwarf plant. You get all tall in the F1 generation. When that is a self-fertilized, you get a tall and the dwarf in the ratio of 3:1. Here they are showing the gametes. This is the phenotypic ratio. What is called a 3:1 is the phenotypic ratio. 1:2:1 is the phenotypic ratio. So he concluded that the inheritance of a character is by particles called hereditary units or factors. These determiners occur in pairs and may be alike as in pure breeding tall plants and dwarf plants. This is referred to as a homozygosity, and they may be unlike and in the monohybrid, which is referred to as the heterozygosity. Okay, so I will give some explanation for this. Each and every character is controlled by a pair of factors he is telling, and that factors he is designating by 2 letters. Okay. Once again, there are different type of nomenclatures are there. Don't bother about that. See, some people designate the dominant allele, say, tall like this and dwarf like this. Now, what is the idea behind this? Dwarf, D is the first letter for the dwarf. Now that is written in the capital uppercase. Okay, then that represents the dominant gene. So this is sometimes written like this, and many methods are the tall is represented like this and the dwarf is represented like this. Sometimes in many of the foreign books you would have seen that it is always written by what is called a plus and minus symbol. Normally they don't confuse. Okay. Now, when you represent the tall and the dwarf like this is called as a homozygous condition. This is also a homozygous condition, and this is a heterozygous condition when 2 alleles of the different types are there. One more terminology is there, hemizygous condition, which you will come across in the sex-linked inheritance, where when you get a particular character in the X chromosome and you don't get that particular allele in the Y chromosome. Now this character is in the hemizygous condition, the hemophilia, color blindness, all these things. See, in man it is represented by only 1 allele. It is in the hemizygous condition. So it is like this. So homozygosity, heterozygosity and hemizygosity. These terms you have to be very clear in your mind. And of course we have got a lot of things to know about this with the help of the dihybrid cross, as well as what is called as trihybrid crosses, and a little bit or little more of this I will be discussing in my next lecture. Thank you very much for patient hearing. Thank you.